Hello, my name is Mark Lubman, and together with Dan Levy, I'm going to explain the importance of the Bernoulli equation. The Bernoulli equation is a sum of the pressure head, elevation head, and velocity head, where the conservation of energy techniques are used. This equation represents the change of energy, but each term of the equation is represented by unit length. Below, you'll see the traditional Bernoulli equation. First, we have the pressure head, which is the head needed for defined pressure. Next, we have the velocity head, which is the head needed for desired velocity. And lastly, the elevation head, which is the potential energy in terms of length. As biological engineers, we're going to be looking at the Bernoulli equation through an agricultural application, where we'll be measuring energy through a pipe used to irrigate crops.
Hey, this is Dan here, and this is the Bernoulli equation used for irrigation piping. Within an irrigation pipe, velocity is typically limited to less for 5 feet per second, which makes the velocity head insignificant and is dropped. However, we must account for the pump energy, which is ht in this equation, and the friction loss, which is HLA/B. Additionally, the units for pressure head are length, and we transform it to be pressure times 2.31, and in this case, 2.31 is a conversion factor where it is 2.31 represents the amount of feet per psi. So this whole calculation will be in British units. This is an example of the Bernoulli equation where you see it's a pipe that runs from point A to point C. At point A, you have an elevation of 100 feet, and from A to B, it's a 100-foot pipe, and then at point B, it's an elevation of 85, and then from B to C, it's a 200-foot pipe, and the elevation of C is 110 feet. There's a pressure at C that's 50 psi, and for the whole system, you have a flow rate, Q dot, of 10 gallons per minute, and the pipe type is a PVZ class 160, that's 1 inch in diameter. And in this problem, we are going to find the pressure at point A. You can see here that we have our traditional equation set up, where we have our height at A, which was 100 feet, our 2.31, and pressure A is what we're trying to find. And HT is 0 because in order to have an HT, you need to be going through a pump, and there's no pump in this problem. Then at C, our elevation was 110 feet. Our pressure at C was 50 psi. And then at the end, we have our friction loss. Now, our friction loss is defined as length times Fc, where Fc is the friction loss constant. And basically, we have you can see in the past, our whole pipe length is 100 to 200, so 300 feet. And in order to find our friction loss, we use our two given informations, which was our pipe, which is 1 inch PVC class 160, and our flow, which is 10 GPM. Now, using this chart, we basically match up GPM on the left-hand side, which is 10, to the inches, which is 1 at the top. And we can see when we match those two up, that our FC comes out to 1.27 psi per 100 feet. Now, once you have that given info, you basically multiply 300 times our constant 1.27, which gives us 381 psi per 100 feet. And in order to get this into feet, you have to multiply by your constant 2.31 feet per psi, which gives us 8.8 feet. Now you just plug in 8.8 into your equation, and you basically set it up and solve for PA, which your PA is the pressure at A, the beginning, is 58 psi. Now we can see that the Bernoulli equation is a very strong equation because piping has a lot of applications, and as long as you have your factors for your elevation head, pressure head, and velocity head, you can basically solve for any sort of situation. I'd like to thank you for taking the time to listen to this video today, and I hope you have a great rest of the day.